Paper 1, Specimen 1. An acidified solution of NH4VO3 reacts with zinc. Explain how observations from this reaction show that vanadium exists in two different oxidation states. So a transition metal can change its oxidation state. So there's certain things about transition metal. It's got incomplete 3D orbitals. The electrons, those 3D electrons, can be promoted or excited, either of those two words, and move between the 3D orbitals, and in doing so absorb visible light. And in absorbing visible light, whatever's remaining, either transmitted or reflected from the sample, is then the colour that you see. But when they change oxidation state, then they absorb different wavelengths of visible light. So the two different colours are observed, which shows the vanadium has changed its oxidation state, or in a different oxidation state for each coloured solution. How a coordinate bond is formed: an electron pair from a ligand. They're the molecules that surround the central transition metal, can donate a pair of electrons to that central metal transition ion. That metal transition ion in the middle forms coordinate bonds with the ligands, but the electrons for those coordinate bonds, coordinate bond, remember, is a covalent bond, but both electrons have been donated from the ligand. Describe what you observe when dilute ammonia is added dropwise. So you've got to know this table. So ammonia dropwise to copper. So copper H2O6. When you add ammonia, first of all, you get the hydroxide, because NH3 forms ammonium hydroxide, NH4OH. So always forms the hydroxide first. So you're going to get a blue precipitate. It's a solid because, as I said before, Cu2 plus, OHs, two OHs, two OH minuses, 2 plus and 2 minus leaves no charge. No charge means it's a solid, and copper is blue, so it's a blue solid. What then, and the first equation then is that. That's what it does first of all. The copper, the 6 waters get replaced by, not by ammonias, they form OHs, CuH2O4OH2 as a blue solid, and I've said NH3 in water makes ammonium hydroxide. So there's the hydroxide part, and it forms ammonium NH4 pluses, and then you've got to balance it. What then happens is that if you add more of it, only the copper does this. Copper can have the 2 of the waters and the OH minuses replaced by NH3s. So 4 NH3s come along, replace 2 waters and 2 OHs, and it's now 2 plus charge, because you've got 2 plus on the copper, as you've always got. H2O2, no charge. NH3 is no charge, so there must be 2 plus left over, and it's a deep blue solution. So that's the equation there. CuH2O4OH2, 4 NH3s come along, they join on as ligands, replace 2 of the waters and 2 OHs, form 2 plus, so now it's soluble in a deep blue solution, and the 2 OH minuses come off and the 2 waters come off. You've got to learn that. When the complex CuNH3,4H2O2 plus reacts with 1,2-diaminoethane, and you've got to remember 1,2-diaminoethane, ethane, C8 with 2 carbons, amino is an NH2, it's an amine group, and it's 1, 2, 2 amine groups, diamino, 2 amine groups, 1 at carbon number 1 and 1 at carbon number 2. So it's NH2, CH2, CH2, NH2. That acts as a bidentate ligand, as each of the nitrogens has got a lone pair of electrons that can form a coordinate bond or a dative bond with the copper central transition metal ion. So each of these is a bidentate ligand, can form 2 coordinate bonds. So it says it replaces the ammonia molecules, the ammonia ligands, but not the water, so it's going to replace all four. But you would only, they've got 4 coordinate bonds, but you'd only need 2 of these bidentate ligands to replace the 4 monodentate ligands, which are the NH3s. So 2 of these replace the 4 ammonias, and then coming off are the 4 ammonia ligands. Suggest why the enthalpy change for the reaction is approximately 0. Well, you should know that when you break bonds, you put energy in. When you make bonds, you get energy out. Well, if you look at the total number of coordinate bonds, it's the same. 6 in each case, coordination number 6. So the same number of bonds are broken as are made. So overall, there is no real energy given out or taken in. Explain why the reaction in question 8 occurs despite having an enthalpy change. Well, there's something else called entropy. Entropy is disorder, where things tend to get disordered. Think about your bedroom maybe. It's all tidy one minute and then disordered the next, possibly. And then you've got to put work back in to get it tidy again. Things naturally go into a disordered state. So that's just the way of the world. So entropy means there's disorder. So if we look on the left, there's 1 molecule and 2 molecules, 3 molecules, making 1 molecule and 4 molecules. There's 3 molecules on the left and 5 molecules on the right. With there being more molecules on the right, there's more entropy change. And entropy change, if it goes more disordered, you make more molecules, then the entropy change is positive, and therefore something called Gibbs free energy change is either negative or 0, and a reaction is feasible and will go ahead.